Well, thank you very much, Jeff. And what a wonderful celebration. Happy birthday, Yakir. And still they gazed, and still their wonder grew, that one small head could carry all he knew. Happy birthday, Yakir. The 13th of April, 1895, was a morning when the Norwegian explorer, Fridtjof Nansen, had good reason for feeling very pleased. He had just set the record for the closest approach to the North Pole 6 days earlier, and now he was moving over unbroken ice to Cape Fligely and home. Until he realized that he had forgotten to wind up his clocks. And therefore he didn't know his longitude, and he was sufficiently concerned about the danger that he took a very circuitous route, which meant that he didn't meet up with others until June the following year. And the clocks needed winding not because of a deficiency in their manufacturer, but because clocks have to be wound. And in order to be accurate, they have to dissipate energy and generate entropy. And the first half of what I want to tell you about this morning follows on directly from the last talk yesterday afternoon from David. So there's wonderful continuity in the conversation here, because we actually have made measurements about the minimum entropy that a clock needs to generate and its linear dependence on the accuracy with which you want the clock to tell you the time. So I want to talk about a whole range of things, from clocks to qubits, and to start off with the thermodynamic cost of timekeeping. And these are just some of about 35 media stories about the Physical Review X paper in which we published the results. Now, the interests go back a bit earlier than that, because for some years we'd been working on this rather miraculous molecule, nitrogen at C60, in which a nitrogen atom sits inside a carbon cage without reacting chemically for all the world like an almost perfectly isolated nitrogen atom. Are you trying to do something for me?
Yes, I'm sorry that I...
What are you trying to do?
Can you put...
Of course I can. There we are. How do I pinch it? Like that? Oh, I'm going to put it that way around, if I may, because that's the way the shirt goes. Is that good,
yeah,
Lev?
If it's pink, it's good. Yes.
Is that good? Okay. So this almost perfectly isolated nitrogen atom, which would otherwise not be feasible because in a gas they find a friend and react with it very strongly, gives a very, very sharp electron spin resonance line. And what we predicted theoretically was that if you reduce the magnetic field to the point where the Zeeman splitting of the electron is sort of comparable with the hyperfine interaction, then you ought to be able to find a clock transition at which the frequency is to first order independent of the field. Those are the predictions on the left. The normal way of doing electron spin resonance is with what's called the B0 field perpendicular to the B1 field. And there the matrix elements for the clock transition vanish. So you need to have the B1 field, the microwave field, parallel to the static field. And if you do that, you can actually find these clock transitions. And here's a close-up of the transitions at the field where, to first order, the frequency is field independent. And that discovery and the associated patents led an American entrepreneur to found a company called Locator X to commercialize it and exploit it. And I get the rucksack with the logo on it. Now, this led us to think about more fundamental things, because if we're trying to make that clock more and more accurate, we try to reduce the dissipation mechanisms. We try to increase the T1 and T2 times so as to get a sharp line and the longest coherence times. And the question is there a limit to that? Or can you go on and on getting the energy dissipation down to nothing? And one of the great thinkers of the second law of thermodynamics a century ago was Arthur Eddington. And he was thinking about this curious phenomenon of our experience of the arrow of time in a world whose physics is almost all time symmetric, with only one exception, that's heat, the second law of thermodynamics. And he wondered if the consciousness, with its insistence on time's arrow and rather erratic ideas of time measurement, might be guided by entropy clocks in some portion of the brain. And duration measured by physical clocks, he thought, might only be remotely connected. Well, is he right or is he wrong? So to look into that sort of question, we developed experiments on the thermodynamic cost of timekeeping. And I'm going to show you there's no free minute if you want to measure it. So you've got in this cartoon a hot bath and a cold bath and a clock. And these minimum amounts of entropy that must be generated if you're going to measure time accurately, and the amount of entropy is proportional to the accuracy with which you're trying to measure the time. I won't go into the derivation, it's in the paper if you want to, but I can sort of tell you how it works. Here's a very simple toy model where you've got a hot resistor and a cold resistor, and a magnetic, electromagnetic resonance circuit between the two of an inductor and a capacitor that have a frequency and a quality factor. And if you go through the maths, you find that to work that as a clock, the accuracy, which is defined as the number of ticks before you are out by one tick compared with what you should be, that's what n is proportional to the entropy generated per tick. Here's a toy experiment that's slightly closer to the one I'm going to show you. So now instead of an electromagnetic resonance circuit, we've got a mechanical resonance circuit. And as the mass on the spring moves, so it alters the capacitance, which gives you a way of measuring the position of the mass. And in this case, it's more or less the same formula, except that we take into account that the amplifier may have noise associated with it too, which may be greater than the Johnson noise of the second resistor. So that's where that second formula comes from. And the important point is just the proportionality between the accuracy and the entropy. So the actual experiment was done with a little silicon nitride membrane. And it's in an electromagnetic cavity. And we put in artificial heat in the form of this noise power. It's white noise power there. And then we have a circuit on the right, which is really a sensor circuit to measure the position of the membrane. And out of that, you get a signal which oscillates at the frequency of the membrane. And you can measure the ticks as they go past. In the experiment, what we actually did was to digitize the whole signal and then do the analysis subsequently numerically. And here's the sort of data that we get. This is an extraordinarily difficult experiment. Do not try it yourself at home. It's very hard because the quantities are so small. But the different colors are for different powers in the measurement circuit. That's not so important. The more power you have there, the more accurately you can measure when the ticks occur. The important thing is this horizontal scale here, which is the white noise power that we're putting in. And the key result is that as you increase the white noise power, so you increase the accuracy of the clock. And by looking at the sidebands in the detection signal, we can deduce the entropy generated, and we can compare that with what you would predict from this formula. And I'm sorry, we're a factor of 10 out, but then this is a limiting formula. and there are all sorts of other factors that may be coming in that maybe we could improve with a better experiment. So the scales here are different. Nevertheless, this linear relationship is rather well substantiated, and frankly, given how tiny these quantities are, we were quite glad to get it right to within a factor of 10. So that's the key message so far in this talk, that to measure the time, you have to dissipate entropy. There is a thermodynamic cost to measuring time, and therefore in terms of Eddington's original conjecture, we'd have to say, actually, it doesn't have to be anything special about human consciousness. It doesn't have to be anything special about mechanisms that take place in the brain. Anything that measures the passage of time will give you time's arrow because of the entropy generated. So, oh yeah, you've got a question.
Can you say what about the difference between quantum accuracy and classical accuracy?
I can't hear you. You'll have to speak up, please. You could press your microphone.
I was asking if you could say a word about this difference between quantum accuracy and classical accuracy. In particular, the quantum accuracy doesn't have H bar.
Oh, sure. The first and the main difference between the formulas is that you can't have an amplifier in a quantum clock. But the quantum clock does have to operate on, well, for example, people have done experiments on a quantum clock that operates as a sort of Otto cycle. And when you do the analysis of that, you get the formula on the left without the extra noise or temperature because of the amplifier.
So what value of H bar will take me from, or any parameter will take me from the quantum accuracy to the classical one?
There isn't, well, there's not an H bar in that formula there.
Right. That's what I'm surprised by.
Yeah.
It's quantum, but there's no H bar.
Pardon?
This is what I was surprised by, that it's
Yes.
a quantum formula, but there's no H bar that separates between the two.
Yeah, maybe it is remarkable. There have been some rather nice experiments done in the University of Queensland that have tested the quantum clock accuracy. And actually, they were done after us, but they got closer to the theoretical model. Yeah, you had a question.
Yeah, I kind of wanted to follow up on that. I was wondering whether the sort of dimensionless form of the quantum accuracy means that the fundamental limit is simply that you need to dissipate on the order of one bit of information, one bit of entropy for every tick. Because at every tick, you have to make sure that you don't reverse the evolution.
Yep, yep.
Forward.
Yes.
So 1 bit per tick, something on that order sounds natural. But for the classical accuracy, the extra formula is this ratio of two temperatures, which is Tn.
Tn is an effective temperature that takes into account the noise in the amplifier in addition to the Johnson noise in the second resistor. Okay. And yeah, I mean, you can sort of see that if you turn this round, you're going to get that delta S is the Boltzmann constant times a number over here. So you can sort of relate that to the Landau erasure, can't you? Okay. Paul.
Andrew, can you also relate it to the work of Jarzynski and Crookes, so you have a formula there for the ratio of a system going forwards and a fluctuation taking it backwards.
Yes.
You know, how often will it go back the wrong way? Seems that there must be some close connection here, because your clock, you know, so long as it ticks in the right direction for n is fine, but if it jumps backward,
Yes,
that's
yes,
bad.
yes.
You know, there's got to be a link, I would think, because that's related also to the dissipation.
Well, I love that approach, Paul. We haven't done that calculation, and it would be lovely to do it. And one of the problems for us experimentalists is we feel a bit outnumbered by the theorists in the room here. So it's a bit like being a lion in a den full of Daniels, or maybe a den full of Daniellos, maybe I should say. But let's explore that, because what I want to do is to go on to show you how we can investigate the thermodynamics of very small systems. Because if you think of conventional, 19th century thermodynamics, it was for an Avogadro's number of molecules with a gazillion states that they could be in. And one of the things that Chris Jarzynski has done is to say, well, what happens if it's actually only one particle or very few particles, and only maybe 2 states it could be in, or very 2 states, only a few states. And of course, the exciting field of the quantum thermodynamics of the very small is, and what if it could be in a superposition of those states? So that's the kind of thing that we're now setting up to evaluate using a different kind of resonator, a very small nanotube, suspended between, could be a hot and a cold source, or it could be 2 electrodes with different chemical potentials. And this goes back to some experiments.
Are you aware of the words of Sandro Popesco about the smallest quantum time machine, heat machine? He did very...
Well, Sandu's here. He can tell us about it. Where's Sandu?
No,
Yeah, he hasn't
not
shown
yet
up yet.
coming.
Pardon?
Not yet coming.
I suggest that we defer that question, Yakir, to when he's here,
Okay.
and let him talk about it himself. Of course, it's always terrifying when you're giving a talk here and Yakir says, "Are you aware of?" Because usually you're not. So these were some experiments we did yonks ago to measure the elastic properties of a nanotube by using an atomic force microscope and a sort of Swiss cheese kind of sample holder with holes in it. And what we want to do is to do the tiny analogy of the 19th century thermodynamics, which was used for developing steam engines. So you've got that up there. I suppose there should be a cold heat bath as well. Forgive me not having that in the circuit. But what we've got here is we've got a quantum dot in the nanotube, which could be an electron spin up or spin down, but in the experiments I'm going to show you it's either not an electron or an electron there. And then the way of storing energy is the motion of the nanotube here. And that's the sort of experimental setup we've got. And one of the crucial features is that as the nanotube moves, so the energy level between the ground state and the excited state changes. And that's crucial to the operation of the whole thing. So this is an electron micrograph of the actual sample. The nanotube's about 2 nanometers across, so it's about a 50,000th of the diameter of one of the hairs on your head. And a crucial bit to get your head round is how Coulomb blockade works. If you've got a quantum dot in the nanotube with, for the sake of discussion, 2 energy levels, which could be due to quantum confinement, but they don't need to be. They just need to be because of the quantized charge on the electron. Then if there's no energy level between the Fermi level of the source and the drain, then no current flows. It's called Coulomb blockade because of the Coulomb charge on the electron. On the other hand, if you move that, which you could do with an electrode, moving the energy levels, then current can flow. And if you keep doing this and you've got lots of levels, you get oscillations like that. These are Coulomb oscillations. And similarly, you can move the Fermi level in the other direction of the electrode. And if you keep doing this, you get what's called a stability diagram. So this is the bias voltage up here. It's the difference in voltage between those two. And this is the gate voltage, which is effectively like moving this up and down. And you get these regions here of Coulomb blockade where no current flows, and then these other regions where either a negative or a positive current flows. So this is the actual experimental setup, zooming in from the dilution fridge. I don't know if you've noticed that in all the pictures of quantum computers, the fridge is always open, because that's when it looks photogenic. But if it's open, it's not working. So it's actually much better to have the fridge with a boring grey shield around it, which means it's actually working and the experiment's running. And then you can zoom in to successive levels to the little device. This is a real experiment. So it has a real circuit. That's why if theorists are visiting us and they say, could you easily do such and such an experiment? Regardless of what they're suggesting, the answer is no, because no worthwhile experiments are easy. They're all difficult. Just to simplify that one a bit, let me show you the three experiments I'm going to demonstrate the results of. One is where we scan the gate voltage and scan the bias voltage and measure the differential conductance. The next one is where we scan the gate voltage and scan an applied frequency and measure the output power. And the third experiment is where we simply vary the gate voltage, nothing else, and measure the, with a network analyzer, the transconductance as a function of frequency. So here are the results. The top one is the first of those experiments, and you see the Coulomb diamonds. And if you look very carefully, you see there are a few purple bits where there's negative differential conductance. The second experiment is where we're scanning both the gate voltage, which we always are across the horizontal axis, and the applied frequency. And you see that the applied frequency, the resonant frequency, is a function of the voltage, particularly with dips where we have what's called a Briggs-Wigner resonance, where the current's flowing. It's almost as if we're measuring the change in stiffness of the wave function of one electron as we go through the Briggs-Wigner resonance. And then the third one is the most remarkable of all, because here we're not applying any frequency at all. We're simply applying a rather small bias voltage, varying the gate voltage, and you see that the device goes into spontaneous oscillations. And you can think of that in various ways, but the key to all this is that there is inevitably an asymmetry in the tunneling barriers, and in particular there's an inevitable asymmetry in the rate of change of tunneling with energy between the two barriers. And when that's just right, it leads to these self-oscillations. One way of thinking about it is that in the equation of motion, the damping term goes negative. And below the threshold, if you look at the thing in phase space, you just sort of get a spot in the middle. Nothing's happening very much. But if you go above threshold, there's a sharp resonant peak, and it's a sort of coherent oscillation, as evidenced by this donut in phase space. And you can begin to think of analogies with lasers. It's not a perfect analogy, but there are some similarities. Well, the next slide I put in just for Howard Wiseman. Where's Howard? Over there. Because I know, Howard, how you're interested in bistabilities in nonlinear systems. And one of the things that we've found in more recent experiments is that this thing does go nonlinear. It does have bistable regions. The left-hand picture is for a single dot, like the previous experiments. The right-hand one is where we create a double dot in the nanotube. And we find these regions of bistability and hysteresis. And then the last result that I'll show you without much comment is that we've achieved the regime where there's ultra-strong coupling between the electron population and the mechanical motion of the nanotube. Ultra-strong in this case means that the coupling strength expressed as a frequency is about 2.5 times, more than 2.5 times, the frequency of the motion of the nanotube. And that opens the door to a whole family of experiments of the sort that you were asking about, Paul, and indeed some of the ones that you were talking about in your talk yesterday, like little nanoscale Szilard engines, and we hope one day a quantum Szilard engine. When you look at this thermodynamics of timekeeping, you find that there's a strong link to the thermodynamics of a learning machine. It's easiest to see it if you think of a spiked neural network learning machine, but it applies to other learning machines as well. And just as there is a minimum thermodynamic cost to timekeeping, which is proportional to the accuracy, so there is a thermodynamic cost to the learning process. We have that in everyday speech. We learn by trial and error, okay? That's entropy cost. We learn from our experience of making mistakes. That's entropy cost. And that can be quantified. And in so much of our experimental work, like the LIGO experiments that we were learning about, Bill was telling us about yesterday, you spend all your life trying to minimize noise. You don't want noise. Get rid of noise. Noise is a bad thing. If you get rid of noise in a learning machine, it learns at 0 rate. In other words, it doesn't learn. So noise is an essential resource for the learning process. And one of the people who's analysed this very carefully, not least while he was with us in Oxford last year, is Gerard Milburn. And he's been looking at the thermodynamic cost of learning. Here are a couple of figures from a paper that he wrote in Oxford last year. This is the thermodynamic cost of learning a NOT gate. And the change in entropy is the change in error here. So if you're going to have a reduction in the error of your learning machine, there's a thermodynamic cost that goes with it. A particularly interesting case is the XOR gate. The XOR gate you cannot learn by support vector machines and so on because it's not separable as a Boolean table. And there's the thermodynamic cost of a XOR gate. This, of course, is simulation, but watch this space because soon we're going to have experimental results that will test these ideas, rather as we did for the thermodynamic cost of timekeeping. Well, that brings me to the end of the first point that I wanted to talk about, which is these thermodynamic costs of clocks and learning. So just a little break. You may know that a lot of the original thinking about all this was stimulated by Maxwell's demon thought experiment. And one of the students, Brendan Severin, has actually built a little Maxwell's demon game. And 3 years ago, we showed this to the advisory board of my laboratory. And for the next week, the advisory board were all playing this game and trying to get the best score they could. So you're welcome to go to GitHub and play the game. Don't do it during any of the talks today, please. And you have to see how low you can get the entropic cost. And it takes into account the entropic cost of erasing the information after you've made an observation and decided whether or not to open the gate. So that's just some fun. So if you're happy for me to... I wonder if anybody could Jeff, you couldn't get me a glass of water, could you, very kindly, or just a water drink? That's really kind. Sorry to have a slight frog in my throat. That's most kind. Thank you. Thank you.
Andrew, are you going to transition to a different topic entirely?
Yes.
I have a question,
Please.
related to this.
Yeah.
For a long while, the most accurate clocks in the universe were pulsars, and they are indeed very accurate. They're also dissipated because they emit radio pulses, and that's about their only dissipation. And we know the period, the spin down rate, and we know the energy dissipated. I wonder how well that would fit in, just how accurate is a pulsar.
Wouldn't it be lovely to calculate that?
It could be done in 10 minutes.
I love it. Let's follow up the question. David.
This is a related question. Very naive question. Please excuse the naivete. I'm trying to make a sort of straightforward conceptual connection between timekeeping and increase of entropy. Suppose I have like a pulsar. Suppose I have a very heavy sphere, but not radiating, turning at a certain definite angular velocity out in intergalactic space, a solid sphere. It seems like a very accurate timekeeper. I don't see any increase in entropy going on. What's going on?
Well, that's a good question. I don't know the answer to that. I only know how to do experiments, and we're quite good at doing experiments in the lab on little tiny membranes. We're not quite so good at putting black holes in our dilution fridges and testing those.
But isn't the answer that a clock, to be a clock, you've got to be able to read out? Because you don't have to have a sphere in
I don't know, so you have a sphere with a little mark
A
on
simple
the
harmonic
equation.
oscillator in quantum mechanics.
Yeah.
But if you're going to read out,
Yep.
then there's going to be a cost.
Wait, and then does somebody have to shine a light at you? And does somebody have to shine? What is it when the time has been recorded?
From the object to you.
No,
And
no,
the
no.
rotation may do some Doppler
I
shift.
don't understand.
And it may
Does somebody then have to shine? When is it that the time is recorded by the device? Only once you know it, or does somebody afterwards have to shine a light on you? And then does somebody have to shine a light on the person who shined a light? I don't understand. What is the time measurement over?
we have to get information from the rotation body.
So there has to be a
Someone-
conscious being?
Not conscious.
So what?
No, no, no.
Some detector.
But the
some
detector is the sphere.
Okay.
I don't understand.
I'm gonna move on because I love these discussions. Yeah, one last question, then I'm gonna move on.
Okay. Thank you so much for giving the time to the question. Yes, that's now it's you consider that's right entropy cost in that can be taken as the time sometimes cost of the timekeeping, but in that just only that focusing on accuracy of the timekeeping there. But normally that's another timekeeping is just the stability of that the some of the accurate on that the clock is moving. But the completely different than other.
Completely different.
Yeah, completely different. This is that the stability of this that's the moving on that's the clock.
Oh, but it's like a steam engine. You can do much worse,
Yeah.
but you can't do better than that. That's the point.
Yeah, but it does not indicate on the accuracy. Normally, that's the some that's the community on that's the timekeeping community, time clocking community that around this around derivative such kind of such kind of indicator we use.
Yes.
But in that the case, your discussion only focusing on the accuracy only.
Yes.
At the one time in that to keeping the time clock, to keep timekeeping, that is okay. But long time is the behavior of the timekeeping.
Yes.
Is we should take care of another indicator.
Well, there are lots of things that go into the accuracy. Okay. And most clocks are not limited in this way. It was extremely difficult to do the experiment where you reach this limit.
Yeah.
And you can see why that is, that at room temperature, we're talking about quantities of zeptojoules,
Yeah.
and at cryogenic temperatures, we're talking about quantities of yoctojoules. I mean, these are tiny quantities, and they're very difficult to measure. And I beg your pardon?
Remind me of a yocto.
10 to the minus 24, okay? And that's a difficult quantity to measure, right? And so most clocks are dissipating far more energy than that. What's really hard is to get down to the point where it's this fundamental limit that's really constraining you,
Okay.
okay?
Yeah.
I'm going to move on because I'm making a segue now to learning machines. And I'm particularly interested in telling you about machine learning for quantum computing. And this one picture shows you why this is a really hard challenge. This is illustrating the challenge for, there are lots of ways of doing quantum computing. This is a particular implementation whereby you have two quantum dots, each of which has one and only one extra electron. And the quantum information is encoded in whether the state is a singlet or a triplet. And in a typical device in the lab, you've got about 8 voltages that you're controlling to get it right. A typical device, the voltages might vary from 0 to minus 2 volts. And there's about a 2 millivolt range for each of those voltages in which the device will operate as a qubit, okay? So you've got a haystack that's 8-dimensional, and the needle is 1,000th of the length in each of the 8 dimensions. And that's what you're trying to find in the haystack. And this is, you can't illustrate more than 3 dimensions at best, but this is a little illustration of how you're trying to look for that. Humans can do it, obviously, because humans have been building elements of quantum computers since before we developed the machine learning for the job. Just to give you some idea of the scale of the operation, this is from the World Economic Forum State of Quantum Computing last year. They reckon about 30 billion pounds, or dollars, probably US dollars, investment in quantum computing. According to them, they reckoned about half of that was in China, which may be right. The map's already out of date. The UK has gone up to 2.5 billion pounds. This is the startups that are coming. Look at the change between the smaller, darker blue circles in 2015 and the larger, paler blue circles from 2 years ago. Another way of displaying the data from a more recent report, McKinsey, shows the number of startups has grown to about 250 or more by April this year. And here they've done it as a function of time and separated it by the kind of activity that's being undergone. At the turn of the century, David De Vincenzo articulated 7 requirements for quantum information processing. The first 5 were for building quantum computers, and the last 2 were for quantum communication. And it's still too early to say which of the candidate implementations of quantum computing might eventually dominate. This is a survey from last year that Michel Mosca and Marco Piani do each year, of what they call the Quantum Threat Timeline Report. And you can see the top 5 candidates: superconducting, trapped ions, cold atoms, quantum optics, spins in silicon. And what you notice there is that there's no consensus as to which is the leading candidate. And even the one at the top of the list that makes the most headlines, the superconducting systems, less than half of the experts that they questioned thought that, ranked that as the lead candidate. What's developed in the years since the De Vincenzo criteria is that people have realized that you've not only got to get the good qubits that have still got to satisfy, roughly speaking, those criteria, they've stood the test of time, but there's an awful lot of classical stuff that has to sit on the stack that you've got to get right if you're going to build scalable quantum computing. So here's a list of the sort of requirements that you might now think that you're going to have to satisfy if you're going to build a quantum computing industry. I think we're going to see a lot of activity around the hybridization with high-performance computing, but I particularly want to focus on this requirement, number 3, the quantum control methods. And you can illustrate it graphically like this, that you've got the quantum processor down there. It's in a cryogenic environment. You've got the control electronics. And the bigger you try to make this with the more qubits, the greater is the need for automated tuning and characterization. And on the right, I've put there some of the companies that make some of those components in the stack. And this is a challenging job. From the same Quantum Threat Timeline Report, these are the timescales that the experts estimate to having a scalable logical qubit. And again, there's a wide range of opinions. There's no consensus. But you've got to get 10 years out, and even then, less than half the people think that there's a more than 99% certainty that you'll have a logical qubit by then. 50% certainty looks like, sort of 3 to 5 years away. Maybe we'll do better. This is predictions, and as we learnt yesterday, predictions are very difficult, especially about the future. This is, well, you may know that one of the things that really released dollars, particularly in the US, for quantum computing was the prospect of breaking public key cryptography, code breaking. This is from last year's report, the experts' opinion on when that will happen. And you see, you've got to get 15 years out from now before there's a sort of consensus that it's about 50% probable. And if you want something more than about 80 or 90% probability, well, according to those experts, it goes out about 30 years. The machine learning will accelerate this development because it will speed up the scalability of computers, it will speed up the improvement in the fidelity, and rather crucially, it will speed up the uptime where the qubits stay in tune and don't need a human to come back and fiddle around with them. So this comes from merging the two hot topics of machine learning and quantum technologies. So what we want to do is to be able to take things all the way from a fabricated quantum chip through to an optimized qubit. And you can think of that in two stages. The first one is using machine learning just to get a qubit at all, and the second one is to get it optimized. And in the work we've done in our lab, we divide this into various different stages. The first one is the sort of coarse tuning, to get to the point where the thing's roughly working, all the way through to the fine tuning where you've got optimized quantum coherence and performance. Our workhorse qubit is the double quantum dot with the quantum information encoded in whether it's a singlet or a triplet state. But I'll first of all show you some results just from tuning up a single quantum dot. So that's the very first stage of coarse tuning. And there's no one technique called machine learning. It's a whole discipline now, and we use different tools out of the toolkit for different stages of the operation. So it's not a person with a hammer looking for everything to be a nail to hit it with. And the first stage, we use what's basically Bayesian optimization. And some of you will know how Bayesian optimization works. You have a belief, a prior belief. The belief is shrouded with uncertainty. And what you do is you make a rather quick and cheap calculation of which next measurement will do you the most good in reducing the uncertainty. That's called an acquisition function. So in this case, it says make the measurement there, so you make the measurement there, and then you make a new estimate of the acquisition function. So here's an example where we're doing that with these Coulomb diamonds for a single quantum dot. And basically what the machine does is it makes a sparse number of measurements, and then on the basis of its pre-training, it makes a series of predictions. And the predictions deliberately have some variability. And it says, well, where is the variability greatest? And you can imagine it might be at the edge there. And here are a whole series of predictions. If you made a measurement there, you wouldn't learn very much, because all the predictions are more or less the same there. But if the machine makes a measurement here, it learns a great deal, because the different predictions are different. So up there is the acquisition map, and down here is an acquisition line for that, and you can turn that into a map. So let me show you that actually working. All our experiments are the machine controlling experiments in the lab in real time. So these are all real experiments, 64 sparse measurements on the basis of prior training, an acquisition map, and where it's the darker purple, that's where it's going to make the measurements first. And now you can see this evolving as the experiment runs. And then last of all, it makes the measurements where there's no current flowing, because that's where it's going to learn the least. Here's another example. This is more like that haystack that I showed you earlier on. Down here, no current flows at all, so it's pretty flat, doesn't learn much. Up there, the current flows whatever the voltages are, so it doesn't learn very much. Here's the interesting region, where you might have one and only one excess electron. So that's where it makes the measurements first. So that's the early sort of coarse tuning stage. Let me now illustrate. Yeah.
What's the goal here? Is it to find the best Coulomb blockade point, or?
Oh, thank you. That's so helpful. I'm accelerating a bit because I'm looking at my watch, so I should have slowed down. In this particular case, we're simply trying to characterize it. In the next example I'll show you, we're actually trying to tune the device to where we want it to be. But this is an important stage of the tuning, because having characterized it, the machine then knows that this is where it's going to find the good operating region. So that comes... Pardon?
What do you mean when you say that's the place where you could find the good region to operate?
I mean where you've got, in this particular case, because it's a single quantum dot, one and only one excess electron in the dot. If you've got gazillions of electrons, it won't work as a qubit. If you've got no electrons, it won't work as a qubit. But if you've got one, then you're in business.
And does it do it faster than a graduate student?
Watch this space. Watch this space. I'll show you the answer to that question. I'm just going to show you one other method that we use later on for the fine-tuning. And this is now much more like conventional deep neural networks that you may be familiar with. This is where the device is tuned. This is now a double-slit device, and it's tuned to a region where, oh, it's beginning to look quite good. The characteristic pattern here is hexagons and then triangles within the hexagons. So now it's feeling that it's quite close, and we're ready to use this kind of technique. And this picture here is what a well-tuned device will look like, with two dots and one and only one electron in each dot. And now we're going to use just a rather conventional deep neural network. So you have an encoder. You take the raw data here through a series of nonlinear transfer functions. You reduce it to a smaller number. This might be, you know, cat over here and dog over there, or something like that. Then you do a general adversarial network, and then you have a decoder that can reconstruct the cat from that. And this is the sort of thing that's widely used on the web now. So here's how it actually works in our case. We've got the encoder. We bring it down to this plane, and we have a position in the bottom plane of a target one. This is a very well-tuned device. This is really good. And what you do is you compare the actual measurements you've got with the target, and you want to try to reduce this distance in the bottom plane. So that's what the algorithm does. It learns how to twiddle the knobs of the different voltages. And I can show you this actually working. Again, this is the code actually working on an experiment in the lab. So the left-hand side is the target. The right-hand side is the tuning process happening. And you can see the series taken from that movie there. With here, it's a rather well-tuned device. Now, you asked, how does it compare with a student? Typically, a student might take a few days to do this. If they're a beginner student, they might take a week or two. If they're a very experienced researcher, they might do it in half a day, or perhaps less if they get lucky. This is machine learning. So it's the machine learning how to tune. So whereas in previous computer programming, you would have programmed the computer to control the experiment or to perform a task, now you program the computer to learn how to control the experiment or to perform a task. And one of the ways that we wanted to try this out was to try it out on 3 different architectures. They're all silicon or silicon germanium double dot devices, but 3 very different architectures. And the rule we gave ourselves is that we could retrain the algorithm on the different structures, but we would not touch the algorithm itself. So no changes to the algorithm. How well could it learn how to tune each of those 3 architectures? Remember, at best, a human can do this in some hours. So here are the 3 architectures, and that's how long it took for each of them. And these are now rather old data. It's now rather faster than this because it's got better at it. So I've shown you quite a number of results. There are some of the people who contributed to them. By the time of the pandemic, these methods had been adopted by laboratories well, apart from Oxford, 4 other laboratories. And we reached the limit of our ability to meet the demand, because, you know, we're academics, we like helping people, we like collaborating with people, but we'd reached the limit of our capacity to do that. So that's why we founded the company Quantrolox, and it's now grown to 20 people. It was founded, we're celebrating almost exactly the 2nd birthday of the founding of the company. It's had more in grants than any other spin-out at Oxford at this stage in its development. And the product will be launched the day after Yakir's 91st birthday in Munich. I think I'm going to pause there. I could go on to talk about the ethics of AI, which I'm very happy to do, and it's something I'm passionate about. But before I do that, I'm quite happy to pause for questions on the science before I go on to the ethics, or I might not get onto that at all. You might rather discuss the science. Yeah.
So, can I go back to the first part of
the first talk?
Okay, so this is related to the time measurement and the entropy.
Yep.
The example you gave on quantum dots is, I find very impressive, because it talks to people like me coming from condensed matter physics.
Yeah, I'm not sure that you've got your microphone on. I'm having difficulty hearing you, or perhaps you can speak more clearly.
Now, okay, can you hear me now?
Yes?
Okay, so I found your example of quantum dots very appealing to people like me coming from the field of condensed matter. But frankly, I didn't understand that example. The point, if I understand correctly, you want to enhance the accuracy by generating more entropy per tick. And tick would be a passage of an electron from, let's say, the left side to the right side. So that will be 1 tick. So it stands to reason that if you increase the voltage bias on this system, there is more entropy generated. However, the process inherently, the process of tunneling, is stochastic. So never mind the fact that you have higher voltage, you cannot overcome the stochasticity of that. So I don't understand how you can overcome the, or how you can improve the accuracy.
Right. So the machine learning, we were not applying that to clocks. We were applying that to getting the population right in the quantum dot. In the case of the spontaneous oscillations in the carbon nanotube, there, you're quite right, of course, the tunneling is stochastic, but let me just go back to that and show you what I mean. This may be a good way to show it, all right? So what happens here is that as the nanotube moves, so it's moving closer or further away from an electrode. And that has the effect of shifting up and down the energy levels within the quantum dot. So as it moves, I don't know which way it is, but let's say as it moves closer to the electrode, so the energy levels might shift down. And now if you've got an asymmetry between the tunneling rates of the two barriers as a function of energy, depending on which way the asymmetry works, you might get more electrons tunneling off. The rate of tunneling off might be faster than the rate of tunneling on. So the mean occupation decreases. So then the attraction of that quantum dot to the electrode might decrease, and it moves away. But now as it moves away, the energy levels move in the other direction. So now we might find that the rate of tunneling on increases faster than the rate of tunneling off. So now the charge on the quantum dot increases. So now it moves back towards the electrode. And that's the source of the energy in the self-oscillations. So that although each individual tunneling event is stochastic, we're altering the tunneling rates and the tunneling probabilities by the position of the nanotube.
So what you're saying is that you create a dynamics where each tick consists of a larger number of electrons that go from left to right, and therefore you improve the statistics. But in order for the number of electrons that go from left to right to increase in each tick, you need to generate more dissipation, namely you generate more entropy. That's the story.
I suppose that would be true. I mean, we didn't actually use this device for the clock experiments, all right? The clock experiments were on a different kind of device where there was no relevant tunneling, and the source was entirely white noise, which we used as a sort of synthetic kind of heat. So you can think of the white noise as temperature, but we actually synthesized it with white noise. So that was the clock experiment. I don't know, we'd need to put the numbers in. My guess is in these experiments, the energy scales are so vast that you'd never detect these tiny entropies, but I'm not sure about that.
If we can have another clock question to tie what you were talking about to the next talk. So if you have a quantum oscillator and it's just left on its own, unitary evolution, and we believe that it would be a good, simple harmonic oscillator, be a good timekeeper. But it's not a clock because you need to read out the ticks.
Exactly.
And that collapses the wave function that dissipated. But now, supposing you have a weak measurement approach, you try to sort of sneak a look at where the pendulum is at. So
yes.
With a large ensemble. You know, how does that play out with the entropy? Because now we have to look at the vanishing dissipation across a large number.
Yes.
It seems like somebody in this room ought to be able to.
I think that's right. I'd love to see a proper analysis, but I'll gladly tell you what my intuition is. Can I tell you my intuition? So this is unsupported by evidence. My intuition is this, that the detailed analysis that George Nee and I did of the weak measurement was that it gave you no benefit. In all but the most contrived of cases. You can contrive cases where it gives you a benefit. And the reason is because in the case of the spin of an electron turning out to be 100, what you're doing is you're not comparing this curve with the same curve shifted by a factor of 100. You're comparing this curve with that curve, right? And so by the time you've done enough measurements to get the same signal-to-noise ratio, you haven't won anything. Right. My guess is that doing weak measurements on the clock, you'd find that by the time you'd made enough measurements to get the same accuracy, you wouldn't have won, and you'd end up with the same entropy output. That's my intuition.
And that's mine as well, but it would be interesting to see it.
Indeed. But I think nothing would please me more than the sort of things that I've been rabbiting away about this morning, stimulate people to do some really good new theory on these things. Yeah. I hope that'll happen. Yeah.
So I wanted to ask you on the quantum dot stuff as well. So you said that you're looking for more dissipation because I know there are...
Have you got your... Can you speak up?
Yeah, I will try. So So there are protocols which you can use to decrease dissipation. So you can like find optimal work extraction from like a single electron box or quantum dot, right? But you're saying that you want the opposite process. So I was wondering if you can use machine learning or like some analytic tools to find protocols which will give you like maximum, the opposite limit, like maximum dissipation.
Well, now you've touched on a lovely intuition, another one that I have, which is that I think almost every aspect of physics that we do, can benefit from machine learning. And I'm just going to show you, what's gone wrong with this thing? There we go. I'm just going to show you one slide here, which comes out of a detailed discussion that we had about this at a conference in Obergurgl earlier this year. Jörg Schmiedmeier and I had convened it. And we had a very detailed process for identifying aspects of physics that could benefit from machine learning in ways that we could foresee. And this is a sort of table which is in the process of being refined through consultation of the community. And I'd love you to look at this table and say to yourself, which of those do you find it plausible that machine learning might help in research in those areas of physics? And indeed, what would you like to add to that table? Because I'm sure it's not complete. So I think this is a rich area to investigate. I see someone photographing it. I'll gladly share the whole paper with you if you'd be interested. Because I think this is a rich area, and I think there will be aspects of our physics research where the machine learning could become as significant a tool as the computer is for doing calculations and simulations already.
There is the possibility of having nuclear clocks with isomers, which will be even more precise. And then, because it's nuclear levels, the dissipation will be higher.
Oh, absolutely. In fact, I skipped over the detail, but even in that nitrogen, endohedral nitrogen, we actually switched from the dominant isotope, nitrogen-14, to nitrogen-15 because it's better. It's only got spin 1/2 rather than spin 1. So I absolutely, let's look for these materials that will give us better clocks. And of course, just simple radioactive decay is an amazing clock, all right, which is used by paleontologists all over the world because it's such a fantastic clock. They can do their dating of past rocks and fossils and things using that. So there really are a wide range of these clocks that are available. I think one of the ones that's understudied is the simple thermal clock. So you can just run a clock just with a temperature difference between two places. In fact, there are lots of ways to do it. I beg your pardon?
No, I was
Jeff is the chairman of the session.
okay.
But now I'm in a terrible moral quandary. Lev is up next. Talk about robust.
I would not want to eat into Lev's time. I want Lev to have his full time, but I do long to discuss these things with people in the breaks and over the meals and drinks and things.